Hi everyone, welcome to Integrated Photonics Lab. In the first video, I make an advertisement of my lab, and in this video, I'd like to talk more about research. So here's a brief introduction of integrated silicon photonics with on-chip lasers. I will talk about what we have done and what we are trying to do in this field. You're most welcome to know more about this lab through our website, and hopefully this video will generate some mutual interest for possible collaborators and future students to join this group. So what is integrated photonics? Integrated photonics can minimize optical functionalities into a compact form factor and allows for the improvement in performance as well as reduction in terms of size, weight, power consumption, and cost. So the photonic integration relies heavily on the choice of substrate material compared to the traditional 3-5 substrates such as gallium arsenide or indium phosphide. Silicon provides more than an order of magnitude reduction in price per area with high throughput processing, good thermal and mechanical properties, and can leverage from the most advanced CMOS processing. Over the development for the past 2 decades, silicon photonics has been very successful in datacom and telecom, and is growing rapidly in other applications, including LiDAR, gyroscopes, biosensors, and spectrometers. So in addition to the CMOS control, and one important feature of silicon photonics is the low loss silicon waveguide with dB per centimeter scale optical loss and excellent optical confinement. This laid the foundation for low cost, high density, and high volume photonic circuits, and a variety of photonic devices are now standardized in multiple CMOS photonics foundries across the world, including modulators, switches, low loss waveguides, detectors, MEMS, etc. However, the indirect bandgap of silicon and germanium make them inefficient light emitters for high-performance lasers. Currently, the best group 4 laser has a special current density as high as 300 kilo-ohm per centimeter square, which is orders of magnitude higher than what is achieved in the direct bandgap 3-5 materials. In addition, devices made from silicon and germanium can only cover modulation and detection for wavelengths around the near infrared, but are not suitable outside that range. Silicon is reciprocal, so isolators and circulators are not possible. As a result, to overcome the inherent limitations of group 4 materials for gain, efficient modulation, and detection at wavelengths outside the near infrared, requires we integrate silicon materials together with the 3-5 materials. So to integrate 3-5 devices, especially lasers, onto the silicon substrate, there are 3 integration approaches depending on how we use the substrate. So the first one is hybrid integration. This is a well-established method where different chips were fabricated with separate substrates and then packaged together through optical coupling. So flip chip bonding is one example, and this integration normally happens at a device level or die level. So one advantage of hybrid integration is the capability to optimize active and passive separately without sacrificing for process compatibility. However, optical packaging with optical alignment often occupies over 90% of the total cost. So the alignment process is very time-consuming and limits the overall device's throughput. Heterogeneous integration, on the other hand, can bond the unpatterned 3-5 thin films to the silicon wafer at the early to middle stages with the cost alignment, and then we can define the device lithography on the full wafer scale. So the integration can combine materials and create a layer structure that cannot be directly grown or formed together, and support parallel processing of a large number of devices. So the overall efficiency is very high, reaching coupling loss lower than 0.5 dB per interface. And this process has been so successful that after 10 years after demonstrating its invention in USB back to 2016, Intel has already introduced its own family of 100 gigabit per second transceivers based on heterogeneously integrated lasers. And ever since then, a total of over 6 million 100 gigabit optical modules with heterogeneous integrated on-chip lasers has been shipped and generating over $1 billion of revenue. So however, you still have to use the 3-5 substrates for the laser growth. That can be costly, and the limits in limitation on the maximum bonding size, set by the largest available 3-phi substrate, which is typically no more than 150 millimeter for indium phosphide and 200 millimeter for gallium arsenide, which is much smaller and expensive than the silicon counterpart. So at this point, the choice of a substrate becomes very important in the overall cost. And monolithic integration through direct epitaxial growth as a more economical, favorable option for integrating laser source into photonic chips. And also, it can provide the best natural heat sinking of laser operation. However, there is fundamental material difference between a 3-phi and silicon during epitaxial growth, which can generate high densities of crystal defects, including primarily the spreading dislocation densities, the stacking force, and anti-phase domains. So these defects act as non-radiative recombination centers that grow with device operations and into dislocation network, and finally large network darkline defects that can degrade the device performance and shorten the lifetime. So while research has been conducted since the 1980s to grow quantum well-based lasers directly on silicon, the aging tests show the maximum device lifetime of quantum well lasers on silicon less than 200 hours. And in this scenario, how can we improve 3-phi lasers on silicon by orders of magnitude? So the first strategy is to deal with the active region, and a quantum dot can be used instead of quantum wells. So what is a quantum dot? You see. Okay, it's not working. So quantum dots represent the zero-dimensional particle in a box-like quantum confined structures that can be formed through a self-assembled process using indium arsenide on gallium arsenide layer. So you see this variation in density states with degrees of quantum confinement. So the modification of the quantum confinement results in redistribution of the low electron states over the energy and the momentum, which means you have changed the shape of density states. And when the active layer has quantum confinement in 3 dimensions, in the case of quantum dots, a complete localization of electron and holes can give rise to this sequence of delta function-like states possessing analyte degeneracies, where a large number of states available to carry it in a small energy range. And thus, quantum dots can promise a lot of performance advantages over its quantum well counterparts, including a very high temperature tolerance that can allow robust CW operation up to 220 degrees C, which is sufficient for datacom ambient environment. This very low spectral current that is capable to support a low energy consumption, the reduced lateral diffusion that enables the scaling of laser cavities to narrow reach or high surface area to volume ratio micro cavities, which is important for high integration density and platform volatility. And also ultralight enhancement factor that makes the device insensitive to reflections. So you don't need isolators that are bulky and expensive. And also a high four-way mixing coefficient that allows for multi-wavelength mode like laser lighting with high channel count and excellent RF performance, which is a great candidate for comb lasers. And one very important feature is reduced lateral diffusion, which can greatly improve their tolerance to crystalline defects that will I would like to especially emphasize. So as previously described, the heterogeneous integration can generate a large density of spreading dislocations that act as non-radiative recombination centers and grow with device operation. So in the case of relatively high spreading dislocation densities, which is seen by these red curves, the carriers in a quantum wells are free to move around with the plane and encounter this defect and recombine radiatively. But in a quantum dot, the carrier diffusion length was reduced from tens of micron to just like 1 micron, and can greatly reduce the carrier mitigation due to dislocations and their chance to be trapped by the dislocation trap states. So here is a more vivid example. So in this TEM image, the red points refer to the spreading dislocation, and the yellow dot refers to the quantum dots. And you can see that even with a very high density of spreading dislocation density, so there are a lot of red spots. But because the dot density is still more than 2 orders of magnitude larger than the dislocation density, and each dot is independent. So one defect in the active region can only kill 1 or few dots, and the majority of the dots are not affected, so the device can still work efficiently. And in addition to changing the active region from quantum wells to quantum dots, the second strategy is to reduce the defects in semiconductor material itself. So remember, we just mentioned that the fundamental material difference between 3-phi and silicon can generate this kind of high density crystalline defects. Different polarities create any-phase domains, different lattice mismatch creates spread dislocations and stacking force or misfit dislocations. And to deal with the any-phase domains, these any-phase domains, so people find that a thin layer of gallium phosphide buffer can efficiently suppress the defects. And nowadays, 12-inch gallium phosphide silicon wafer are commercially available with no any-phase domains, and to deal with spreading dislocation densities. And a symmetry step graded filter was invented, such that surface defect density can be obtained as low as 1/6 by both Aki and the plain view TM. And to combat with misfit dislocations, a thin strain quantum wells can be inserted as trapping layers above and below the active region, which can efficiently block 90% of the misfit dislocations away from the active region, which is experimentally confirmed by the cell measurement. So together with these great innovations in the growth to combat any-phase domains, the spread dislocation densities, and misfit dislocations, high quality 3-phi buffer can be achieved on CMOS compatible 001 silicon substrate. So this much improved defect density, tolerance of quantum active region, together with the much reduced defects in the semiconductor material, can give rise to record long device lifetime on silicon. While the maximum lifetime record the quantum well lasers on silicon has only 200 hours after several decades of research development. Our generation 1 quantum dot device can show a lifetime of 800 hours at 30 degrees C, and later 100-year lifetime at 35 degrees C for generation 3 devices, and over 8 years at 60 degrees C for generation 4 devices. And most recently, we show meaning our extra lifetime at 80 degrees C. So this is a remarkable improvement compared to our first generation devices, and it's also orders of magnitude longer than any of the previous lifetime tests of quantum well lasers grown on silicon. And this excellent reliability makes heteroarchitecture growth to be truly considered as an integration platform, and we are warranted to investigate into more advanced laser configurations, which can be needed for more practical applications. So with the time entering the realm of commercial relevance, there's a lot of recent progress of quantum dot devices grown on silicon, such as the ultra-low spectral optical pumped photonic crystal lasers, the sub-million spectral electrically injected microwave lasers, carbon cavity tunable lasers, these Moloch lasers, ultra-low dark current fault detectors, and high gain, high saturation optical power semiconductor optical amplifiers. So in optical transceivers, the power consumption of the laser can comprise a significant fraction of the total transceiver power budget. And microcavities can be perfectly to solve this issue, which confine light to small volume with resonant recirculation, which is a very advantage to make ultra-low threshold and small footprint light sources. However, this previous demonstrated quantum well-based microcavity lasers can experience a series of sidewall scattering and recombination as the resonant size is reduced to tens of microns, which can result in either a faster rollover, increased threshold, and relatively low operating temperature. So quantum dots, at the other hand, has reduced sensitivity to recombination at device sidewalls and other surface defects. And by combining the Wisdom Gallery mode cavity with the carrier localization of quantum dots, the oblique compound device has a size as small as 4 micron in diameter, threshold as low as 200 microwatts, and can be scaled to sub-wavelength scale with cavity sizes as small as 0.5 micrometer in radius, and a threshold as low as 35 microwatts, and extracted spontaneous emission factor as high as 0.3. Compared with optical pumping, electrical injection is more challenging for the micro lasers because electrometallization is limited by the micro-size cavity. And with a special etching recipe and a sidewall passivation technique to form a 4 micron tool mesa with a straight etching profile and a smooth sidewall surface, we have this electrically injected microwave lasers, which has some median threshold and maximum operating temperature up to 100 degrees C. And more importantly, you see in this figure, it shows how the spectral current change with a reduced cavity radius. And we can see that even at the smallest dimension, which is set by the limit of our lithography tools, the spectral current still shows monotonically decreasing, indicating there is a very low impact of excitable recombination. So this kind of downscaling capability and this compact geometries and very low power consumption is very promising for high density and a low power photon integration. In addition to microwave lasers, wide tunable laser is also a very important branch of lasers that provides backup transmitter sources and components of wavelength routing devices. So the traditional tunable lasers use quantum wells as actuation and are typically fabricated through regrowth steps on native substrate or integrated on silicon through wafer bonding techniques. So these kind of structures typically require complicated fabrication and a relatively large footprint and multiple electrodes for wavelength tooling. And here, we use a specially designed half-wave coupler as half-mode selection filter, and leverages the quantum dot reduced surface recombination effects to enable deeply etched processes through the active layer. So with this simple and integrable device structure, without using any grading lithography or rigorous process, we demonstrate the first tunable single wavelength quantum dot laser, where we have these two vapor probe cavities have slightly different lengths to shape the Brownian spectrum for wavelength tuning. And we achieve this 40 nanometer wavelength tuning with up to 45 dB centimeter spatial ratio. In addition to the improvement of material quality and individual quantum dot device performance, a lot of efforts are also needed to form a fully integrated photonic circuits. So today, indium phosphide-based monolith integration and silicon-based heterogeneous integration are the two most very important on-chip integration technologies. And quantum dot-based photonic integrated circuits on silicon can thus be built upon what has been achieved through either of these two approaches. So in the first platform, all the photonic functionalities are performed in the spray-form material, and the silicon wafer is only used as a handle substrate. This approach can benefit from the lower substrate cost, the larger wafer size, the lower small impedance of silicon, and the well-established wafer scale CMOS fabrication. And it can be achieved by regrowth, offset quantum dots, intermixing, etc. And following this direction, we previously demonstrated high-performance regrown quantum dot DFB laser integrated on silicon substrates. And by realizing high-quality MB regrowth capability in gallium arsenide-based materials, we can enable the possibility to spatially combine different band gaps into one optical chip. So the DFB structure was grown on an on-axis gallium arsenide on silicon substrate by a two-step MB process. So the first growth stopped at this 100 nanometer UID gas layer on 12 of the active layers, and then a uniform first-order DFB grading was dry etched into this gas layer with an etch depth of 50 nanometer. So here is the SM image of the surface grading, and the grading quality and the following pre-rigorous surface treatment is very important, and they are stringently controlled to achieve high quality regrowth of the rest part of the laser structure. And after that, the material was processed into deeply etched waveguide structures. So this is the temperature-dependent Li curves of the representative device, showing CW rating up to 70 degrees C and a characteristic temperature of around 85 Kelvin in the low temperature range. We had this single mode operation sustained in the ground state across a wide current range of 110 milliamps with a maximal centimeter spatial ratio of more than 50 dB. So emission wavelengths from 1285 nanometer to 1338 nanometer are covered by a laser array on the same chip. And with an increase in temperature, the spectrum position the mode slightly shift at rate of 0.086 nanometer per Celsius without mode hopping. And intrinsic line width in the device was measured to be 480 kilohertz, and in our latest round, this value was reduced to 10 times smaller. So compared to the state-of-the-art result from other groups, the monolithic quantum dot DFB laser represented here has better performance in terms of threshold, power, and temperature stability. And most importantly, intrinsic line width of tens of kilohertz is pretty low compared to typically solitary quantum well laser line width, which is several megahertz. So by virtue of the small line width enhancement factor of quantum dots, we are able to perform a system demonstration without optical isolators, and we got an aggregate transmission capacity of 640 gigabit per second, which is achieved by using the 5 channels of the laser array with a 64 gigabit PAM4 modulation. So the current wavelength range was limited not by the quantum dots, but rather by the range of grading periods we currently use. So using a chirped design in the quantum dot region, the gain bandwidth can actually be experimentally broadened to 127 nanometer. So the laser wavelength can also be extended well beyond the current test range, and a 1 terabit per second data transmission is achievable without an isolator. And for the second direction to integrate quantum dot-based photonic array circuits on silicon, we not only use silicon as a substrate. Actually, we aim to achieve this low-loss active passive coupling of 3-5 with silicon waveguides, and this is something really Silicon Photonics. So in this case, compared to the standard heterogeneous process, it requires changing from indium phosphide based quantum well epi to gallium arsenide based quantum dot epi, and thus we need different material systems and thus very different device designs and process optimization. So for the epi design, we started with the material stack for monolithic quantum dot lasers, and a transition to a design for heterogeneous integration require adjustment of the bottom cladding to accommodate evanescent coupling, which is obtained by removing the lower 40% L-gas cladding and placing the N-gas contact layer directly below the 20% N-gas separate SH layer. So to prevent charge carriers reaching the bonding surface and get a non-radiative recombination, so we adhere to periods of superlattice to minimize the loss, and to allow for resistance, low resistance electrical injection, the N-contact layer was optimized to be 150 nanometer. So here is the schematic showing the quantum dot laser integrated on SOI, consisting of a hybrid 3-5 silicon active region coupled to passive silicon waveguides on 2 ends. So the process starts with paneling the GPV marker, the surface grading, the ray waveguide, the vertical channel, and then direct wafer bonding of the quantum dot wafer to the silicon wafer, conducted using an O2 plasma assisted process, followed by annealing at 100 degrees C for 18 hours. So for the passive silicon waveguide, there are several things to keep in mind. So first, the cutoff wavelengths waveguide weights for the single mode operation and simulated to be around 650 nanometer for the transverse electron polarization. So we keep this waveguide weights in the passive region below 600 nanometer to have a safe margin for fabrication variation in the waveguide weights, and especially in the etching depth. And for the hybrid part, the optical mode is laterally confined by the silicon waveguide, while a portion of the mode evanescently overlaps the 3-5 quantum etch region. So this figure shows the simulated optical mode confinement factor in the quantum dot region and in the silicon waveguide for various silicon waveguide weights. So with the increase of the silicon waveguide weights, the guided fundamental mode is more tightly confined and has less interaction with the edge of the silicon waveguide. This leads to lower scattering loss. And at the same time, the mode is put more into the silicon region, which results in an reduced mode overlap with the quantum dot etch region. So considering both these effects, a trade-off must be made to achieve sufficiently high Moore gain for low threshold laser mode operation, as well as to maintain low scattering loss. And the hybrid silicon waveguide was kept as one micron. And for the surface grading that is formed on top of the silicon waveguide, and the width of the grading can be tailored to achieve different couple design, and thus different radiation loss and threshold Moore gain for the lasers. So for our optimized design, a narrow width of 50 nanometer was chosen, which corresponds to a calculated coupling coefficient of roughly 50. So after the passes waveguide process and subsequent wafer bonding and the substrate removal process, there comes one of the primary fabrication challenges. So to etch the graphite mesa precisely down to the 150 nanometer N-gas contact layer and keep the etching depth uniform across the whole wafer. So for indium phosphide-based devices, we have highly selective wet etch that is available to planarize the mesa etching depth and stop right at the target layer. But this is unfortunately not applicable for L-gas and gas material systems with low aluminum content. So to precisely control the mesa etching depth, the quantum dot graphite mesa was defined in 3 steps. So the first etching step was controlled using a laser monitor to stop around 100 nanometer above the Boron SH using chlorine nitrate. It's the ICP plasma etching. And afterwards, a short selective dry etching comprising of BCl3, SF6, and N2 gases was performed, where we have a high etching selectivity of gas over L gas to ensure that the whole wafer can be uniformly exposed down to the 30 nanometer Boron SH layer. And finally, we do a timed short standard etch to remove the 30 nanometer SH layer and just expose the 100 nanometer N-gas contact layer. So a lot of process optimization was devoted to achieve this smooth and a vertical sidewall so that we can get this very nice graphite taper to shape the hybrid active mode to couple into a passive single waveguide mode on both ends. And after the P-mesa paneling, we continue with a lower N-gas contact layer tapering in a separate short transition. You see here. And then we can deposit the metal stacks as a contact metal for P and N, and passivate the device, open vias, and apply the probe metal. So this figure shows the representative Li curves for a laser bar with a 3 micrometer wide graphite mesa. So the laser had a special current of 6 milliamp at room temperature, which corresponds to a pretty low special current density of just around 30 amp per millimeter for each of the quantum dot layer. And this is the representative emission spectrum, which shows single mode operation with maximal simultaneous ratio of more than 60 dB. And here show the temperature Li curves. We got C double lazy up to 75 degrees C and a characteristic temperature around 103 Kelvin in the low temperature range. And in general, very high modulation bandwidth is very difficult to obtain for quantum dot lasers due to the lower confinement factor and a finite intra-band relaxation time and gain saturation effect. So, today, even the best reported modulation bandwidth of the O-band quantum dot UV laser grown on a native substrate is limited to just around 10 gigahertz. But here we got a record high value of 13 gigahertz here, and just with polished facets, and there is still a lot of room to improve the modulation performance. For example, adding a pervia facet coatings and depositing the metals on a thick dielectric for lower capacitance, etc. So this kind of result is very promising as it shows us a synergistic relationship between the unique capabilities of graphite quantum dots and silicon, which allows for not only a reduced cost due to the economical scale, but also security-wise performance exceeding what can be achieved with purely graphite quantum dots. Furthermore, one important aspect of quantum dot laser is the small alpha factor that contributes to significant reductions in the laser line width. So here the Lorentz line width was measured to be 26 kilohertz, which is an order of magnitude lower compared to the typically solitary quantum well halogens line width, which is several megahertz. So this table compares the device performance of this work and the previously reported work. Again, this table clearly shows that the heterogeneous quantum dot BFB laser with the silicon waveguide can significantly outperform the monolithic quantum dot BFB laser without a silicon waveguide in terms of line width, bandwidth, thermal ratio, etc. Which we are very excited about, since when you put lasers on silicon, you not only get a better substrate, you also get better lasers. So in addition, the heterogeneous quantum dot BFB laser shows promise to compete with the heterogeneous quantum well laser, with many promised advantages of quantum dots in smaller line width enhancement factor, lower threshold, and higher temperature tolerance. So at this point, we get a lifetime entering the realm of commercial relevance. We get a very encouraging device performance and the initial integration trail. So what is missing? For one, majority of the research into epitaxial integration still focus on lasers. More work needs to be done to explore the possibilities of amplifiers, photo detectors, and modulators to prove their performance. And more work needs to be done to integrate quantum dot active regions with each of these components. And for this active and passive coupling and co-integration, we now cooperate with Intel and is using Intel's 300 millimeter silicon photonics platform to pattern the silicon passive parts and to be bound with the quantum dot epi. So heterogeneous integration has been very successful and commercialized in several companies, and Intel has launched mass production lines for data center and applications. So if we changing out the bonded quantum well epitaxial material for quantum dot on silicon structure, there will be substantial opportunities to build upon what has been achieved through heterogeneous integration to both improve performance and reduce cost. And our mission is to accelerate optical I/O technology innovation in performance scaling and integration with a specific focus on photonic technology and devices and small circuits and link architecture and package integration and fiber coupling. So currently, the biggest driver in future developing silicon photonics is still for datacom. But beyond the data center, the dense device integration will be critical for a number of innovation future applications. So for optical phased array based LiDAR, this integration, high power will definitely be a big advantage. For photonic biosensors with integrated light sources, the price will be significantly reduced and the size will be significantly reduced, which is very important for portable devices. So for space applications, radiation damage is a big concern, and a high degree of tolerance to such damage in quantum dot lasers can find applications here. And for neuromorphic silicon photonics, the current approach of fiber coupling is, of course, the most straightforward way to get the light into the chip. But in the future version, especially spiking neural networks, on-chip laser sources will be required so that all optical signals can be confined within an integrated circuit package for the efficiency, stability, and scalability. Furthermore, silicon photonics already show promise as a platform for quantum computing, and quantum dots show promise as a source of entangled single photons compatible with the proposed computation schemes. So this kind of research is still in the fundamental stage. But if quantum dots can be integrated in silicon photonics for classical applications with established process, then it makes sense to grant them extra consideration in designing future quantum computing platforms. So my current work still focus on the device level, and my future work includes active passive coupling and co-integration of lasers for these various applications. So by leveraging the attractive features of integrated silicon photonics, my team aims to develop on-chip lasers in, but not limited to these applications for substantial performance gains, green solutions, and mass production. So thanks a lot for your attention, and look forward to future collaborations if there is a mutual interest, and look forward to prospective students to join the exciting research journeys. Thanks very much.